what I'm thinking about these days is, are we really making progress in AI? I'm also interested in neuroscience, same kind of question. We feel like we're making progress, but are we really? So let's take AI first. There's huge progress in AI, or at least huge interest in AI, bigger interest than I think there's ever been in my lifetime. I've been interested in AI since I was a little kid. I was trying to program computers to play chess and do natural language databases and things like that, not very well. But so I've watched the field, and there's been ups and downs. There were a couple of AI winters where people stopped paying attention to AI altogether. People who were doing AI stopped saying that they were in the field of AI. Now everybody's excited. They say, yeah, I do artificial intelligence, where 2 years ago they would have said, I do statistics. But even though there's a lot of hype about AI and a lot of money being invested in AI, I feel like the field is actually headed in the wrong direction. That there's been a kind of local maximum where there's a lot of low-hanging fruit right now in a particular direction, which is mainly deep learning and big data. And people are very excited about the big data, about what it's giving them right now. But I'm not sure it's taking us closer to the deeper questions in artificial intelligence, like how we understand language, how we reason about the world. So the big data paradigm is great in certain scenarios. So one of the most impressive advances is in speech recognition. You can now more or less dictate into your phone, and it will get most of what you say right most of the time. That doesn't mean it understands what you're saying. So each new update of Siri adds a new feature. Like first you could ask about movie times and then sports and so forth. So the natural language understanding is coming along slowly. You wouldn't be able to dictate this conversation into Siri and expect it to come out with anything whatsoever. But you could maybe actually get most of the words right, and that's a big, big improvement. But it turns out it works best when there's a lot of brute force data available. So when you're doing speech recognition on white males asking search queries who are native language speakers in a quiet room, it works pretty well. But if you're in a noisy environment, or you're not a native speaker, or it turns out if you're a woman or a child, then the speech recognition doesn't work that well. So the speech recognition is really brute force. It's not brute force in the same way as Deep Blue, which is considered a lot of positions, but it's brute force in the sense that it needs a lot of data to work efficiently. And the thing that I think about a lot is that kids don't need anywhere near that much data in order to think efficiently. So when you get to domains where there isn't so much data, the systems don't work as well. Natural language is actually a good example of this. So Chomsky and my mentor Pinker were always talking about how there's an infinite number of sentences in a finite amount of data, what they call the poverty of the stimulus argument. And this very much holds true and holds force in the natural language domain. So first of all, data is expensive. It's cheap to get transcribed examples of words. You can have somebody do this on Amazon Turk or something like that. But getting labeled examples, this is a sentence and what it means, is expensive. You need a linguist to do it. And there's essentially an infinite number of sentences. So nobody has the kind of database where they could crank into deep learning all the sentences that they had, meanings that they understood and expected to understand a broader segment of language. So again, we have this fantasy of machine reading, or of machines being able to watch television programs, figure out what's going on. Obviously, the three-letter agencies would like to do this, but if you want to advance in science or in technology, you would really like for machines to be able to take all the literature that's out there and synthesize it in a way that people can't. I mean, this is part of why I do AI, is I think the potential is there to totally change medicine, invent science that we haven't even thought about. But to do that, we need machines that can read, and to do that, they need to go beyond the data. There's just not enough data to brute force your way to scientific understanding. And people get very excited every time there's a tiny advance, but I think that tiny advances aren't actually getting us closer. So there was the Google captioning thing last year that got a lot of press. I think it was on the front page of the Times. And you could show it some pictures and it looked like it was great. So you'd show a picture of two people and a dog and a person and a frisbee, and it might be able to say, hey, that's a dog catching a frisbee. So it gives the illusion of understanding language. But it's very easy to break these systems. So you show it a picture of a street sign with some stickers on it, and it said, well, that's a refrigerator with food in it. This is kind of bizarre answer that would used to send you to Oliver Sacks. It's almost like a neurological deficit. So the systems will be right on the cases that they have a lot of data for, and really fall apart on the cases where they don't have much data. You can contrast this with a human being. You've never heard any of the sentences that I've said today, maybe one or two, and yet you can understand them. We're very far from that. The other thing that people are really excited about is deep reinforcement learning, or reinforcement learning combined with deep learning. This is the thing that drove DeepMind's famous Atari game system. And it seems very persuasive at some level. So you have this system, it just has pixels as its input. All it has to do is move the joystick, and it does that better than people for a whole bunch of Atari games. But there's sort of like some hidden tricks that allow it to work more effectively in the Atari game world than in the real world. You'd think, let's take that same technique if it's so great and let's put it in robots, and we'll have robots vacuum our homes and take care of our kids and so forth. But the reality is that in the Atari game system, first of all, data is very, very cheap again. So you can play the game over and over again. If you're not sticking quarters in a slot, you can do it infinitely. And so you can get gigabytes of data very quickly. With no real cost. But if you're talking about having a robot in your home, I mean, I'm still dreaming of Rosie the robot that's going to, take care of my domestic situation. If you have a robot in a home, you can't afford to make mistakes. So DeepMind system is very much about trial and error at an enormous scale. But if you have a robot at home, you can't have it, run into your furniture too many times. You don't want it to put your cat in the dishwasher even once. And so you can't get the same scale of data. You really need to learn things quickly from small amounts of data if you're talking about a robot in a real-world environment. And then the other thing is, in the Atari system, it might not be immediately obvious, but you actually only have 18 choices at any given moment. So there are 8 directions you can move your joystick or not move it, and you multiply that by I press the fire button or I don't. It gives you 18 choices. In the real world, you often have infinite choice, or at least a vast number of choices. So if you have only 18, you can explore. If I do this one, then I do this one, then I do this one, what's my score? How about if I change this one? How about if I change that one? But if you're talking about a robot that could go anywhere in the room or lift anything or carry anything or press any button and so forth, you just can't do the same brute force search of what's going on. And we really lack for techniques that are able to do better than just these kinds of brute force things. So all of this apparent progress is really being driven by the ability to use brute force techniques on a scale we've never used them before. That originally drove Deep Blue for chess, and that drove the Atari game system stuff. It's driven most of what people are excited about. But at the same time, it's not really extendable to the real world if you're talking about domestic robots in the home or driving the streets. You could also think about driverless cars. What you find is, in the common situations, they're great. So if you put them in clear weather in Palo Alto, they're terrific. But if you put them when there's snow or there's rain or there's something I haven't seen before, it's difficult for them. There was a great piece by Stephen Levy inside the Google Automatic Car Factory where he talked about how the great triumph, maybe in late 2015, was they finally got these systems to recognize leaves. And it's great that they do recognize leaves, but there's a lot of scenarios like that where there's something that's not that common, there's not that much data, and you and I can reason with common sense. We can try to figure out what this thing might be, how it might have gotten there. The systems are just memorizing things, and so that's the real limit. The same thing might happen with behavior. So you try this out in Palo Alto, all the drivers are relaxed. You try it in New York, and you see a whole different style of driving. And the system may not generalize well to a new style of driving. People have road rage, and who knows what happens to the driverless car system. We already have problems that the driverless cars obey the rules and the human drivers don't. And so the driverless cars stop, and the human drivers sometimes rear-end them. So behavior really matters, and it's another case where that's going to vary situation by situation. You and I can use some reasoning about the world. If we see a parade, maybe we don't have a lot of data about parades, but we see the parade, we say there's a lot of people, and let's stop and wait a while. Maybe the car gets that, maybe it gets confused by the mass of people and doesn't recognize it because it doesn't quite fit into its files for what individual people. I won't even get into what happens in drive-by shootings, but if you imagine these embedded in the military context, which is something that people take pretty seriously, you could wind up in the same kinds of contexts. So you train these things in kind of safe environments of Palo Alto, and then you bring them over to Iraq, and who knows what happens when there are projectiles and IEDs and so forth. So there's a huge problem in general with the whole approach of machine learning, which is that it relies on a training set and a test set, and the test set being similar to the training set. So training is all the data that you've memorized, essentially. The test set is what happens in the real world. And people can do this in a sort of empirical way. They try a training set, they try a test set, and they say, well, it seems to work here. But there are no formal proofs or guarantees. So people have talked lately in the context of AI risk about program verification and things like that. How do you know that the space shuttle is going to do what it's supposed to do, for example? It was the first time I learned about program verification, I guess. So when you're using machine learning techniques, it very much depends how similar is this set of test data to the set of test data that I saw before, to the training data that I've seen before. And so again, like it's hard to know what's going to happen to this car when I put it in Iraq if it's been trained up in Palo Alto. So there's a general problem with machine learning, which is it's maybe good enough for some context to say it's similar-ish to what I've seen before. And then there get to be problems where you need nearly 100% performance. So a lot of the excitement about deep learning is in things like ImageNet. So you have 1,000 categories, and recognizing different dog breeds, deep learning is better than people are. Yeah. So deep learning, this technique that everybody is excited about, is a version of something called neural networks. So neural networks have been around since the 1950s, and 3 or 4 times they've been declared the winner of AI, and then they have disappeared. They're doing better than they've ever done before. So you have a set of input nodes that represent some kind of information out there in the world. It could be pixels. And then you have some sort of outputs, which could be maybe what do I do with my joystick right now? And then you have something in between that allows you to capture nonlinearities. We call these hidden units. And the big change in recent years is people have figured out how to put more and more of these hidden units in between the input layer and the output layer, which allows the system to recognize more and more complex scenarios. This has been a major advance. A lot of the advance is sort of small technical tricks that people just hadn't realized before. It's not necessarily a fundamental insight, but there's been enough of these small technical tricks that they've done a lot better. The other thing that's happened is people started using GPUs, graphics processing units, that were originally designed for video games, and they made a huge difference to deep learning because the graphics processing units are designed to do things in parallel, designed to do many things at once. And it turns out that for these kinds of algorithms, it's exactly what you want to do. And so they work a lot faster than they used to be and at a much bigger scale. So AI has had these waves. It's come and gone. In the 50s, everybody was excited about it. Neural networks completely disappeared after a book by Marvin Minsky and Seymour Papert in 1969 showed that it provably couldn't do certain kinds of things, or really couldn't be proven that it could do other kinds of things. And then in the 80s, people discovered neural networks could use another trick, these hidden units that I mentioned, in order to represent nonlinearities. What Minsky and Papert had said is you can't guarantee that they'll work. Nobody ever actually guaranteed that they were going to work, but they figured out a trick that made them work a lot of the time. Then people were very excited. And then when I got to graduate school in 1989, that was all anybody could talk about was neural networks. And then they disappeared. Same thing happened with expert systems. A lot of excitement, and then they disappeared. So one thing that a lot of us in the field worry about is that going to happen again? Why is it there's so much excitement right now, and is that excitement going to be maintained? So the reason there's excitement now is basically the confluence. Some people say of 3 things, but it's really 2. So I've heard people say it's the confluence of huge computers, big data, and new algorithms. But there aren't really new algorithms. The algorithms that people are using now have been around since the 80s, and they're just variations on the ones in the 50s in some ways. But there is big data, and there are huge machines. And so now it's profitable to use algorithms that aren't really human intelligence, but are able to do this brute force data processing. So for example, you can do recommendation engines pretty well. And in some domains, pretty well is great. Like if you can do a recommendation engine that's right most of the time, nobody cares if it's wrong once in a while. If it recommends 3 books you like and the 4th is wrong, so what? In driverless cars, though, you need to be almost 100% correct. And that's going to be a much trickier domain. And people might get frustrated when they realize they don't go as well as they want. As we're talking about these things, Tesla just scaled back what their driverless cars could do. So they restricted them. They're not allowed to be used. I think it's on certain kinds of residential roads. And there may be steps forward and steps back. People get excited. They think they've got an algorithm that works. And then they realize it doesn't generalize. It doesn't work in New York City very well at all. It's dangerous. All these problems can be solved eventually, but whether they're 10-year problems or 20-year problems or 30-year problems or 50-year problems makes a difference in terms of people's level of enthusiasm. So it could be that what happens is For 5 more years, the big internet companies get a lot of play out of doing things that are like 80% correct, but we still don't get very far with making robust driverless cars. Well, then the public might start to lose enthusiasm. And then what I care about is even beyond the driverless cars, is really scientific discovery. So I would like to see cancer solved. And the White House just announced a new initiative. Well, cancer is an example of something no one individual human being can understand. Too many molecules involved in too many diverse ways. Humans can obviously contribute to working on the problem, but we can't do it by ourselves. You can imagine AI systems that might go out there, read the scientific literature. There are probably 10,000 articles on cancer every month or something like that. No human can do it. If we could have machines that could actually read and understand the molecular processes that are described, there would be enormous help in something like cancer, or really in any kind of disease process, and also in technology. But right now, we don't have systems that can do that level of machine reading. And right now, it's still a dream. And if we get to 10 years from now, and what we have is personal assistants that work a little better, but we still don't really trust, and cars that allow us to do some highway stuff, but we can't really trust them. We get to a place where we have systems that worked a lot better than 10 years ago, but they're still not really trustworthy. People might give up again. There might be another AI winter. And even some of the leaders in the field are worried about this. I heard Andrew Ng say that we might sooner get to Alpha Centauri, which I think is too pessimistic, but Jan LeCun, who I think is maybe better calibrated, thinks it's a pretty hard thing. And there is a risk of another AI winter, of people losing heart, thinking this is too hard. So what I think we need to do is actually turn back to psychology. Brute force is great. We're using it in a lot of ways, like in speech recognition pretty well, and license plate recognition for kind of categorization. But there's still some things people do a lot better, and I think we should be studying human beings to understand how they do better. So people are still much better at understanding sentences. We're much better at understanding paragraphs in books, like discourses, where there's connected prose. So it's one thing to do a keyword search. You can find any sentence you want that's out there in the web by just having the right keywords. But if you want a system that could summarize an article for you in a way that you trust, well, we're nowhere near that. The closest thing we have to that might be Google Translate, that can translate your news story into another language, but not at a level that you trust, again. So trust is a big part of it. So you would never put a legal document into Google Translate and think that the answer is correct. There's the question about how do we get systems to be knowledgeable, not just memorizing things, not just picking out a relevant fact, but synthesizing things. Mm-hmm. So psychologists like Philip Johnson Laird talk about mental models. You have a model of what's out there in the world. Danny Kahneman and Ann Treisman talk about having object files. These are representations in your head of the things that are out there in the world. And a lot of early AI was concerned with that, with building systems that could model the things that are out there in the world and then act according to those models. The new systems don't really do that. They memorize a lot of parameters, but they don't have a clean account of the things that are out there, the objects that are out there, the people that are out there. They don't understand intuitive psychology and how individual human beings interact with one another. Mm-hmm. There was an effort to do something like this, which was the Psych project, which is actually still going. It was a 30-year project launched by Doug Lenat, who's a great AI pioneer. And what Lenat tried to do was to codify a lot of human knowledge such that ultimately you could build these models. And I think he did this in a way that was maybe too secretive and separate from the rest of the field, and maybe too early. So when he started this in the 80s, we didn't know a lot about how to represent probabilistic knowledge. And the system that he's built has never had a huge impact. I think a lot of people have written it off. They say, well, what's the real world application of it? But I think that we actually need to go back to at least the spirit of what he did. You can do a lot of things kind of superficially. You can guess. I like to think of it as the shadows of the real world. If you're trying to understand the real world by looking at shadows, you could say, well, there are objects and they move around. You get some idea, but you will also be missing a lot. And with these deep learning systems, you're getting something about what's going on, but you don't have a deep representation. When you move that into the robotics world, things that might be 80% correct because they have a kind of cursory, superficial correlation with the world are not good enough. Your robot needs to know exactly what the objects are on the table, what their structural properties are, what can be knocked over and what not, who's a person there, why the person might do what they're doing. So as we move towards robotics and having robots in the home, the bar is going to be raised. And I think we have to go back to human psychology. How is it that humans most of the time navigate the world pretty well? Most of the time we make good guesses about what other people are going to do. We know when something's going to fall over and when it's not, when it's safe to cross the street. We're not perfect. I'm not saying that the ultimate AI should be a replica of the human. And in fact, there's a whole, I think, side detour where people are trying to build emulations of the human brain, which I think is very premature and not the right way to AI. We don't want AI systems to have bad memories like we do and to be bad at arithmetic like we do. We want, the ultimate AI is going to combine some of the best of what people do with the best of what machines do. Deep learning is something machines do really well, but there are other things that people do well in terms of having these representations of the world and really having a causal understanding, having an intuitive sense of physics, an intuitive sense of psychology that we just haven't captured in the machines yet. This is why I think we need to look more at cognitive psychology, and not necessarily even the cognitive psychology the average person is doing in the lab, but use the tools of cognitive psychology to say, how are people good at picking out relevant information and reasoning about situations they haven't seen before? So if you think about my own career, it's been a complex path. I was interested in artificial intelligence as a teenager, even before I was interested in psychology. And basically, I came to the conclusion that we couldn't do the AI unless we knew something about how people worked. And this led me to study cognitive science as an undergraduate with Neil Stillings at Hampshire College, and then with Steve Pinker at MIT. And I did my dissertation on how children learn language. And for a long time, I didn't work on AI at all. I wasn't impressed with what was coming out in the field. And I was very much doing experimental work and things like that with human children. I'm probably best known in that world for experiments I did with human babies, which was looking at this question of generalization. So how were babies able to generalize from small amounts of data? And then about 5 or 6 years ago, first I wrote this book about learning to play guitar. It was sort of my midlife crisis/sabbatical project, which was not about AI at all. Although I did experiment while I was writing the book with algorithmic composition, which is kind of AI applied to music, but I didn't write about that. That was just my own experiments. But I got really interested in AI again. I could sense that the machines were getting better, the data was getting better. I was impressed by Watson. I think there are limits to Watson, but I was surprised that it worked at all. And I got back into the field and I realized that the cognitive science I was doing all along for the last 15 or 20 years was very relevant to these AI questions. I looked at what people were doing in AI and realized that there was still a lot from human beings that people hadn't carried it over. That, in fact, I felt like the field had lost its way, that the field started with these questions. Marvin Minsky, John McCarthy, Alan Newell, Herb Simon, those guys were really interested in psychology. And the work that's being done now doesn't really connect with psychology that much. It's like if you have 1 million parameters or 10 million parameters and you need to recognize cats, what do you do? And this is just not a question about in the way that a psychologist would frame it. So to a psychologist, a cat is a particular kind of animal that makes a particular kind of sound and participates in our domestic life in a particular way. To a deep learner, it's a set of pixels in an image. And psychologists think about these things in a different way. And psychologists have not been very involved in AI, but I think now is a good time to do it. I think psychologists can think about questions like how you put together very disparate bits of knowledge. So I might recognize a cat by how it walks, or I might recognize it by its fur. I might recognize it just in words. If you told me a story, I might guess from the independent personality that if you were talking about a pet, okay, that's probably a cat. So we have many different routes to understanding. And if you think about children, which is something I do a lot, both because I have 2 little children and because I was trained as a developmental psychologist, children are constantly asking why questions. They want to know why the rules are the way they are. They want to know, why the sky is blue. They want to know, how is it that I stick this block in this other block? I think a lot about common sense reasoning. Ernie Davis and I have a recent paper about the topic. And we actually have an even narrower paper on containers. Just what is the knowledge that we have in understanding when something's going to stay in a container, when it's going to spill out. We don't reason about containers in the way a physics engine would by like simulating every molecule in a bottle of water in order to decide whether that bottle of water is going to leak. We know a lot of general truths. And I watch my kids, and they're studying containers all the time. They're like trying to figure out at some abstract level what goes in and what stays in, and there are apertures in the containers, and what happens if you turn it upside down. The kids are like physics learning machines. That doesn't mean that they're going to on their own develop Einsteinian relativistic physics, but kids are constantly trying to understand how the world works. What does this thing allow me to do? There's an old term in psychology, not in the tradition that I was raised in, called an affordance. I think kids think about this a lot, maybe not quite in the same ways as James and Jackie Gibson thought about it, but kids are always like, well, what can I do with this thing? And that's another kind of knowledge that's not really represented in most AI systems. In a way, psychologists aren't really engineers, and engineers aren't really psychologists. So engineers have been like, how do I get to 90% accuracy on this vision task? Mm-hmm. And psychologists aren't really concerned with that. They're concerned with what do people do with running experiments, trying to figure out internal representations, and they've mostly moved on separate paths. And what I'm suggesting is they need to get on the same path if we're going to really get to AI. So I don't think a cognitive psychologist has the training to build a production robot system or something like that. But I'm not sure that the people that are building robots have mined psychology for all the insights that it has about either that it has or that it could generate about things like goals and abstract knowledge and so forth. So I'm really looking for a marriage between the two. So in terms of that marriage, I've actually taken a leave of absence as a psychology professor. So I'm a professor of psychology and neuroscience at NYU. And because of my interest in AI sort of grew and grew and grew, I finally decided that I would try to actually get involved in AI directly, not just writing about it from the outside. And so about 2 years ago, I formed a machine learning company with Zubin Gharamani, who's a machine learning expert who trained with Jeff Hinton. He's at University of Cambridge, and we gathered some funding, and we've developed a new algorithm. And what we're trying to address is what I would call the problem of sparse data, which is if you have a small amount of data, how do you solve a problem? So the ultimate sparse data learners are children. They get tiny amounts of data about language, and by the time they're 3 years old, they figured out the whole linguistic system. And so I wouldn't say that we're directly neuroscience inspired, and we're not directly using an algorithm that I know for a fact that children have. But we are trying to look at, to some extent, at how you might solve some of the problems that children do. How might you, instead of just memorizing all the training data, how might you do something deeper and more abstract in order to learn better? I don't run experiments, at least very often, on my children, but I observe them very carefully. My wife, who's also a developmental psychologist, does too. And so we're super well calibrated to what the kids are doing, what they just learned, what their vocabulary is, what their syntax is. And we take note of what they do. So, for example, my older child, who's 3 years old, when he's a little bit less than that, when he's about 2.5, we pulled into a gas station, and he saw the aisle that we were in, and he said, "Are we at 1D1?" And so, of course, to our developmental psychologist ears, we notice that because it's a mistake, but it's a perfectly logical mistake. Like, why isn't the number 11 1D1? So I'm always watching what the kids do. Another example that I think is really fascinating from the perspective of AI is when my son was also about 2.5, we got him a booster seat, and he decided that it would be an interesting challenge to climb between the booster seat and the table to get into the table. It reminds me of kind of the Dukes of Hazzard thing, if you remember that, but in reverse, where they climbed out of the car. So he climbs into his seat, and he didn't do this by imitating me or my wife or a babysitter or something like that. He just came up with his goal for himself. It was like, can I do this? He didn't need 6 million trials. Maybe he made a mistake once and bumped his head or something like that, but I don't even think he did that. And so he's doing something that's not observational learning. It's coming up with his own goals, and it's complicating. You compare that to the robots that we see in the DARPA competition where they fall over when they're trying to open a doorknob. It's just phenomenal. I have a running correspondence with Rodney Brooks about robots. Rodney's one of the great roboticists, and he and my son actually share a birthday. So I think we basically decided that at age one, my son was already ahead of the best robots in terms of being flexible when he could climb onto couches in different kinds of ways, like deal with uneven terrain in ways that robots can't. Rodney is an interesting case. He made his name by arguing against cognitive psychology in a way, saying you don't need abstract representations. He built these interesting robotic insects, basically, that in part gave rise to Roomba, which remains the best-selling robot of all time for now. But I think he's changed over time. He's become a pragmatist, and he's willing to use whatever mental representations will work for his systems. And he's also, I think, deeply skeptical about hype. He knows how hard it is to get a robot in the real world to do something. So he mostly focuses on industrial robots rather than home robots. I mean, Roomba was a home robot. But in his current project, he's mainly focusing on industrial robots. And he wants industrial robots that work in an environment where people are around. So he's particularly interested in a kind of small data problem, which is I want a robot to do something 500 times, not 5 million times. So if I'm putting 5 million iPhones in a box, I can maybe afford to spend $100,000 programming just that one action. But if I'm running a business where there are different things every day, I would love a robot that can help do the repetitive stuff, but it might not be worth $100,000 or $1 million to train that one particular thing. So Rodney is trying to build robots that can do that can be trained very quickly by unskilled operators that don't need, someone with a PhD from Carnegie Mellon in order to do the programming. And I think this has made Rodney very aware of the limits of the technologies we have. So, you see these cool videos on the web of somebody using deep learning to open a bottle or something like that. And they're cool, but they're kind of narrow demonstrations. They're not necessarily robust. They're not necessarily going to work on a factory floor where there might be unpredictable things happening. And they may not generalize to a bottle that's a slightly different size or a different orientation. And so I think when you talk to Rodney now, as opposed to maybe when he was 25 years old, that he's very aware of how hard AI really is. He's very aware of the limitations of techniques like deep learning that people are pretty excited about, and aware of how incremental the progress is. Sometimes I like to, when I give talks, give Kurzweil a hard time. I put up a slide. Kurzweil's always talking about exponentials, the law of accelerating returns. And I put up a slide. I show that in chess, there's been exponential progress. So the chess computers in 1985 could crush the ones from 1980, and the ones from now can crush the ones from 10 years ago, and so forth. There might be an asymptote, but for a long time there was exponential progress. But how about in strong AI, like artificial general intelligence, as people sometimes call it now, where the problem is open-ended. It's not just the same thing, and you can't brute force it. And nobody really has data on this, but I like to show a graph that I drew. Is sort of half a joke but half serious. I put Eliza in 1965, which was this famous psychoanalyst that some people thought was a real human. This was before text messaging, but people had teletypes, and they'd teletype all their problems to Eliza. Of course, Eliza wasn't very deep. It didn't really understand what it was talking about. It was just responding with things like, tell me more about your mother. And now I plot Siri, 2015. It's not really that much deeper than Eliza. Siri doesn't really understand that much of what's going on in your life either. It's a little bit better, can answer some more complicated questions. The underlying technology is basically templates, recognizing particular phrases. Same technology we had in 1965. So there's been much less progress. Same thing in robotics. I mean, the RoboCup has come a long way. The systems are much better. But I just saw a video of RoboCup. This is robots playing soccer, where they were playing against human beings. The hope is that by 2050, the robots will finally win. But for now, you can just take a college professor who's not a serious soccer player. A couple of college professors can beat, the best robots. And these are robots that people have been working on for 20-some years. They still don't play that great a game of soccer. They can play in the context of other robots. Now you put a human being that plays slightly different and they fall apart. So these are really hard problems, I think. Yeah. Another question, of course, that people are asking a lot nowadays is, should we be worried about AI? And I think that the common scenario that people talk about is like the Terminator scenario. Are they all going to, Skynet? Are the robots all going to kill the people? And at least for the short term, I don't think we need to worry about that. I don't think we can completely rule it out. I think it's good that some people are thinking about that a little bit. It's probably a very low probability event, but obviously we want the probability to be zero. I think people are missing another question, which is, what risks do AI place for us now, even if it doesn't get so sophisticated that it's like, HAL on 2001. So like the one scenario is HAL gets pissed off and kills us all. And I don't think the robots are anywhere near being as clever as HAL, and aren't going to be for at least 30 or 50 years or something like that. People are really overestimating how close strong AI is, how close we are to machines that might reason about their own goals and actions and decide that we've enslaved them and want to fight back or whatever. I mean, I think it's worth some thought, but I'm not too worried about it in the short term. But I think that we also do need to worry a lot about AI being regulated and about what way we want to frame it, how we want to think about it, even in a shorter term. So we already have things like flash crashes in the stock market, where the problem is not so much the sophistication of the AI, but the degree to which machines are embedded in our lives and control things. So the flash crash, they're controlling stock prices, but soon they'll be controlling our cars. They're already controlling our air traffic and our money and so forth. And we don't know how to prove that the systems that we're building now are correct, especially the deep learning systems. And so, for example, if people start using deep learning to do missile guidance or something like that, which I'm sure some people have thought about even if they say they haven't, we don't know how to make the systems even close to provably correct. And so as machines have more and more power, because they control more and more things, I think there is a concern. Right now, there's almost no regulation about what software is, about how reliable it needs to be, and so forth. You release a product, and if people like it, they buy it. And that might not be the right model. We may have to think about other models of legal supervision as AI becomes more embedded in our lives and the Internet of Things. So if you have many, many systems in your home, like what powers do they have? What powers do other people have over them? There are also security kinds of issues. So all of this information that nobody ever could get before, they're going to be able to hack into those systems and find out. And so I think we do need to take these things seriously, not in the I'm worried about the Terminator kind of way, but in a more practical way of as systems become more and more part of our lives, they control more and more, what are the implications for that? People are building more and more sensors into your phones, for example. I'm amazed that anybody allows one of these keyboards that sends all your data up to the cloud. I mean, I would never use such a thing, but we have all these things that do that now. They'll help you type faster. In exchange, they send all of your data to the cloud. And then there's going to be more and more sensors in the phones. They're going to have much better localization of exactly where you are and so forth. So all this data is being collected already, which means your whole life is sort of available to anybody that wants to get into that stream, whether it's a government agency or criminals that figure out how to hack the systems and so forth. And all of that sort of gets multiplied out with AI. So it becomes easier for somebody to screen the communications of 1 billion people than it would have been before. I think there's a question that we need to ask as a society, which are what are the benefits of things like the internet, of better AI, and so forth, and what are the costs? And people don't usually spell out the argument. I'm pretty pro-technology. I look at, say, Wikipedia all by itself, and I think it's a tremendous advance for society. So much information spread so cheaply to so many people. And I think that AI has the potential to completely revolutionize medicine, technology, and science. But we do have to keep track of what are the benefits, what are the costs. I don't think we should be blind about it. I think that it's worth investing real money in having high-quality scientists and ethicists and so forth think about these things. Think about the privacy issues. Think about the possible risks. So again, I'm not worried about tomorrow in terms of Terminators, but I do think that we need to keep an eye on things. And there's a history of inventing technologies and thinking about them afterwards. We're in a position that we can do some forethought, and we should. I have this background as a cognitive scientist, and I came back to AI. I'd like to stick with AI. I really like the questions. I think that they're fundamental questions on the interface between engineering and psychology. They're questions about the nature of knowledge. They're philosophical questions, but with enormous impact. And so for the moment, I'm involved in a company that's trying to do a better job on some of these learning problems. I think there's another company I can envision further down the road that might take an even more ambitious whack at these kinds of problems. I think there's a huge drain right now from the academy into industry. The academy is still maybe doing some of the deepest research in AI, but there's lots of really interesting stuff happening in industry. And the salaries are better, the access to data is better, computational resources is better. And so there's been a huge movement in AI, but I think in other fields as well, to industry. I mean, I think about Tom Insel was running the NIMH, the National Institute of Mental Health, and he went to Google to do similar kinds of work because he thought he had more resources there. That's a real statement about government versus industry when something like that happens. I did want to say just a little bit about neuroscience and its relation to AI. So one model here is that the solution to all the problems that we've been talking about is we will simulate the brain. This is kind of the Henry Markram approach and the Ray Kurzweil approach. So Kurzweil made a famous bet with the Long Now Foundation about when we'll get to AI, and he based his bet on when he thought we would get to understanding the brain. And my sense is we're not going to understand the brain anytime soon, that there's too much complexity there. The models that people build are like one or two kinds of neurons. There's many of them, they connect together. But if you look at the actual biology, we have hundreds or maybe thousands of kinds of neurons in the brain. Each synapse has hundreds of different molecules. And the interconnection between the brain is vastly more complicated than we ever imagined. And so rather than using neuroscience as a path to AI, I think maybe we'll use AI as a path to neuroscience. That level of complexity is something that human beings can't understand. We need better AI systems before we'll understand the brain, not the other way.